let's start. Good morning or good afternoon, depending on where you are connected from. My name is Ricardo. I'm a researcher at INESCTEC, and I'll be moderating today's session. Hopefully, you can hear me well. Um, First of all, thank you for joining us at another webinar from INESCTEC Power and Energy webinar series. And sorry for this small technical delay. We had some problems with Zoom. So before we start, a special thanks for Daniela Sá for organizing these webinars, which are actually now on their 21st edition. The previous editions are available online and publicly available on INESCTEC YouTube channel. And so today's topic, as you can see by my presentation, is data markets and sharing in the energy sector, which is actually a very timely and relevant topic in the current IoT landscape. So right now we can find sensors everywhere, from smart meters in the electricity grid to sensors in our homes, in our vehicles, and even our personal devices. So we have data being collected everywhere right now. And of course, besides this being fun, it presents multiple challenges such as data collection, data processing, and data availability, and data, for instance, data rights, property rights, but also opportunities. So you can now collaborate with the others. You can share data with others, and these opportunities will and are and will keep revolutionizing the way that we manage the energy system and the way that we optimize the energy system in the future. So for today's webinar, we will feature two presentations, as you can see in my slide right now. They share some common ground and explore concepts related to data markets, seeing data as an asset, data value assessment, so finding the value for your data, and then how to collaborate within these data sharing environments and how to being incentivized to do so. So you can see here, for instance, he will look into more the parts of looking at data as an asset, the structure of the data market, and even showing a data evaluation framework that integrates forecasting and decision-making processes in multi-energy systems. And Carla will look into more into the algorithmic parts, so developing solutions for data and analytics market, and then the different types of incentives. So you can be paid by your data, but you can also trade data by data in a barter layout. So let me just first introduce our speakers. So we have the first speaker, it is Yi Wang. So he's an assistant professor at the Department of Electrical and Electronic Engineering of the University of Hong Kong. He's also currently secretary at different working groups, as you can see in the slide. His background is on electrical engineering, in which he has a PhD degree. And he is also currently associate editor at multiple journals. And his research focus, as you can expect, is on data analytics for smart grids, energy forecasting, multi-energy systems, IoT, and cyber physical social energy systems, which actually is a very big word, but a very relevant word for the future. The second speaker is Carla Gonçalves. So she's a researcher at the Center for Power and Energy Systems at INESCTEC. She has been participating in multiple R&D projects between INESCTEC and industrial partners. And actually, right now, she's actively participating and contributing to the European projects Enershare and Green Data AI, in which you can find some of the work that will be presented today. Okay, her background is on applied mathematics, in which she has a PhD, and her research focus is on probabilistic and collaborative forecasting and data sharing incentive mechanisms. Okay, so before we move into the presentations, just some words about this webinar series. So they have a very specific goal, which is to present and discuss ideas, outcomes, or results regarding the energy systems of the future. And so we have a specific format for these webinars. So basically we have two sessions, two presentations, each with 20 minutes. And then in the final part of the webinar, we have a Q&A session in the final 10 minutes. So you can make your questions throughout the presentation. You have a specific section for that in Zoom. And then we will read them, we will gather them, and in the end, we will present them to the speaker. Okay? So if you want to present in a future webinar, you can send us an email to energywebinars@inesctech.pt. Or if you want to attend to future webinars, you can find all of them in our website, so energywebinars.inesctech.pt, where you can submit your participation, and eventually we will send you the links to attend to the Zoom sessions. So without further ado, let's move on to E. If you are ready, I think you can start presenting. Let me just stop my share. Okay.
You see the screen now?
Yes. Good.
Okay, great. So thanks for Ricardo's introduction. My name is Yuan. I'm now assistant professor at the University of Hong Kong. My presentation today is smart data sharing in energy systems. So before my presentation, I would like to say thanks to my brilliant peer student, Zhou Yangzhe, who make major contribution to our work presented today. And this work is also supported by RGC of Hong Kong and also National K Research and Development Program of China. So if you want to know more details of my presentation, you can release 4 papers. You can get that online easily. So my presentation contains 4 parts. The first one is the background, and then I will do some simple analysis of the key components of data market, and then I will give a detailed example of data evaluation, especially multi-analysis systems. Finally, I will draw the conclusions and also prospect some future works. Okay, so many countries set aggressive goals about to achieve carbon neutrality. Yes, so it pushes the emergencies of increasing number of distributed energy resources. Just as introduced by Ricardo, that we have a lot of sensors in smart meters or smart grid. So a large number of energy data will be generated and analyzed in the future smart grid and also smart city. So how to define smart? So I think the first one is data, and then we need to find the real value in this kind of data. So that's the smart. So even though we have a lot of data, but they are owned by different data owners. For example, in this figure, you can say, sorry, here. So in this figure, you can see we have a total number of N data owners. For example, electricity retailers, they have their smart meter of different consumers they served. So they have separate smart meter data, but they cannot share this kind of data because of 2 main reasons. The first one is law and regulations. It's illegal. It's probably illegal if to directly share this kind of smart meter data with others because it contains some privacy informations of the consumers. The second one is the business competition. If I share the data with the other, maybe the other will enhance their competitors or in this kind of retail market. So if based on these 2 reasons, I don't, as a retailer, I don't want to share this data with others, okay? So actually, for example, in China, the government put more emphasis on data sharing. For example, the government has issued a series of documents confirming that data is an emerging production factor, reflecting market economy and driving the great waves of the next generation industrial revolution. Originally, we have 4 main production factor: land, labor, capital, and technologies. But now data is the 5th protection. So you can see the importances of data in the future, especially for industrial revolution. So actually in China, there are many cities they have already paid attention to data barriers problem and set up data exchange centers. For example, in Shanghai, in Beijing, and also in Shenzhen, they are the most modern city in China. So actually, it has become a global consensus to facilitate the free flow of data cross borders. For example, in 2021 Digital Economy Report on Trade and Development call for a global data governance approach to facilitate the free flow of data center across the flow of data across border. So you can see that the data market is expected to exist $22 billion in this year, okay, in 2024. We can say we can say this kind of prediction is accurate a lot by International Data Corporation. So the second part is the key component of data market. So in a data market, we have data owner and also data buyer or data consumer. So data owner want to know the selling price of the data, and data buyer want to know the purchasing price if they want to make use of some data from others. So they will be a data transaction between data owner and also data buyer. So we need to establish a market to connect the data owners and also the data buyers in this kind of market. So for data owner, they need to know the data product form. For example, data as a product or data as a service. And we need to know the characteristics of data compared to other traditional product. And also for data buyer, they want to know the purchasing price. They also need to know in which scenario they can make use of this kind of data so that they can make profit. This kind of profit should be larger than the purchasing price so that they can, they are willing to join this kind of data market. So for data attribute, it contains internal and external attribute. For internal attribute, it contains data form and also data context. It's very important to keep the consistency of the data, completeness, and also validity of the data. For example, consistency describes whether the information of the same level is the same in different data sets. They should be consistent. And it should also become completeness. It describes the degree of how many data information is missing. We don't like missing data, yes. And we also want to describe the degree to which the data follow the related rules. For example, that the smart metadata or measuring data in power system should obey the rules, for example, of power flow equations or something like that. So the external attributes are based on the cost driver and also value properties. The value of data is dependent on the applied scenarios. For example, we have several drivers for the cost. For example, construction, operation and maintenance, and also the management. But also this kind of value is highly dependent on the scenarios and also the uncertainties. So in a data market, we have three types of entities: data owner or information vendor, and also information customer is a data consumer, and we also need a data operator. Data provider or data owner are usually responsible for managing, organizing, and also making sense of a great deal of data they connect and also generate data connection equipment, and it can connect a large number of raw data. For data consumer, they will purchase and extract values from this kind of data. So for the market operator, it's responsible for operating the data market, processing the original data, transforming the data into communities, and also publishing data prices, and also, for example, in a clearing market. So that's the basic framework for that. So for the data valuation, the value can be determined from two perspectives. The first one is based on supply-oriented strategy. These kind of strategies are mostly seller-driven, for example, emphasizing the supplier's profit. The demand oriented strategy is related to the expected revenue of the product and also the demand intensity of the consumer. So intensity of demand is related to the quality of data. The expected revenue is the benefit that data bring to the user. So this kind of value can be evaluated from these two perspectives. And we can also have a clearing market to combine these two. So the second one is that market clearing. Different kind of different market structure affect the market clearing. For example, if we form this kind of market as a cooperative game, so for example, game theory can be used to design this kind of project, design this kind of value. So the game can be cooperative or can be non-cooperative. For example, for cooperative game, we can say, okay, that cooperative to make larger profit, and then this kind of profit can be fairly distributed to this kind of data owners if they participate in this kind of market. For a non-cooperative game, maybe there are some collaboration, there are some, in addition to some collaboration, they are more competitive to each other. There will be some negotiation. So we need different kind of game theory to analyze this kind of market. So in the following example, I will introduce a collaborative game-based data valuation approach. This is an end-to-end data valuation in multi-analysis systems. So we know that the power system, gas system, and heat systems are deeply coupled by some equipment, for example, combined heat and power, heat pump, or something like that. So multi-energy loads in this kind of system are deeply coupled, and considering cross-sector information can improve this kind of forecasting accuracy, so that the operational cost of the multi-energy system can be minimized. So if the load data, power demand data, gas demand data, heat demand data can be shared or can be cooperated in this kind of operation of multi-energy systems, maybe they can make additional profit. So in this way, we can value this kind of data. So actually, the economic value of data can be quantified by solving an optimization problem to minimize operational cost. The approach of forecasting and then optimization can handle forecasting and decision-making process as two separately. For example, we can do forecasting first, and then the forecast can be the input of the optimization model. So in this kind of forecast, then optimization strategy, the forecasting model is trained as a traditional loss function as a mean square error. But from this figure, we can say x-axis is the forecast error, y-axis is the additional cost caused by this kind of error. You can say this kind of curve is not quadratic. It's not even symmetrical. So we may need to make a bridge between forecasting and decision making so that we can accurately evaluate the value of load data from power system, gas system, and the cooling system, something like that. For example, if we for traditional load forecasting task, we have the input feature and we have model parameters, for example, of neural networks, and then we also have load forecast. So usually we will do load forecasting task first, and then the forecast will be input of the optimization model, the operational cost is C, and then the Z is the decision variable of the multi-energy system, for example, the operational status of combined heat and power or so on. So traditionally, we will determine omega n for forecasting model first, and then we will determine Z for the operational status first, for the operational status of the multiple energy systems. So in this kind of situation, cross-sector data information has not been shared. They do forecasting separately, okay? So the forecasting and decision process are treated separately so that data cannot directly serve the final decision makings in multi-energy systems. So can we optimize omega n and Z as a whole so that we can integrate the information, the load data, and also integrate the forecasting and decision-making process so that the operational cost can further minimized. So in this case, so if you compare this equation and this equation, you can say here z is the decision variables, but now z and omega n are decision variables as a whole. So we want to optimize these two variables as a whole so that we can encourage sectors to participate in this. So if we want to encourage the sectors to participate in this kind of end-to-end model or this kind of sector, so we want to quantify the value of this kind of data. So we want to answer two questions. First, how many additional value or profit can be derived from data sharing of various sectors in multi-end systems? The second, how to make a fair plan to allocate this kind of profit to each sector. So the first one, how to actually, if we want to load how many additional profit can be derived, we have to optimize omega n, solve this kind of optimization problem as a whole. So an intuitive idea is to train the end-to-end model so that we can use forward and backward propagation. Is very similar that has been used in neural networks. We can do forward forecasting and solve the optimization problem, and then we can do backwards and then backwards. So you can say it's very easy to do forecasting and also solve the optimization problem. And we have off-the-shelf backward forecasting mode, the backward propagation for neural networks. So, but this one is missing. It's very important to how to do backward propagation for this kind of optimization problem. So we want to obtain the gradient of the cost, say the gradient of the cost, say over the load forecast M. And so we want to optimizing a differential neural networks. We call this OPT-LAT. So how to obtain this kind of gradient cost, say over the load forecast M? We can use the Chern, or we can use the Chern principles. dc over dm can be rewritten as dc over dz times dz over dm. So we want to get these two. So if we want to, actually, this is the optimization model for multi-end systems, and then we can write the Lagrange function for this kind of optimization problem. If we want to get a global optimal, then we can write the KKT condition of the Lagrange function if this kind of optimization problem is convex, okay? So we can define the implicit function, and we can calculate gradient z over m, so dz over dm, and then we can calculate this kind of value because dz over dc can be easily calculated. In this way, we can do the backwards propagation for this kind of problem. But usually, OPT-LAT is designed for linear programming or quadratic program problem. But what if there are integer variables in the optimization problem? So we propose a OPT-LAT embedded branch and bound method. So we can incorporate, how about incorporating the OPT-LAT into the branch and bound search process? So you can say in this kind of process, we can do a branch and bound search process so that this kind of search has already embedded in this kind of OPT-LAT to calculate the gradient dc over dm. So even though it has a higher computational complexity, but this kind of practice has higher computational complexity and also storage requirement because we have a lot of branch to search. So in this way, actually we can simplify that. In this kind of model, we can do branch and bound search first, and then do this kind of calculation. If you want to go to detail, you can read our paper recently published in Actual Transactions on Smart Grid. So actually, the additional profit can be quantified by comparing two values. The first one is that the value, if we can calculate the reduced operational cost. So Cn is the operational cost if there's low data sharing. So C C null or so say empty means if all this kind of data can be shared, okay? So in this way, we can calculate this kind of additional profit. So the other one is that how to fairly allocate this kind of data, this kind of value to different kind of participants. For example, power system operator, heat system operator, and also gas system operator. So we can use Shapley value if they can formulate it as a collaborative game. So we can easily calculate this kind of Shapley value by remove some, one or two or more participant in this kind of sharing game. So we can do this kind of Shapley value, calculate this kind of Shapley value. But sometimes Shapley value can be selective. So it's very dangerous because it's selective. If it's possible to be selective, then maybe they are not willing or they don't dare to this participant, this kind of participant in this kind of market. So we will use zero Shapley value. So this kind of zero Shapley value doesn't satisfy this kind of balance. So we will minimize it or normalize it. Okay. So for example, when owning sectors in you participant in this kind of corporation, so how to measure VU? So if we how to measure this kind of value? So we just move it and owning some part, owning the participant part, participant this kind of backwards propagation. If this kind of, for example, if power sector does not participate in this kind of market, and then there will be low propagation, low backward propagation. They just provide this kind of forecast directly. So this is a case study. We do this kind of data, we calculate the daily operational cost for 12 months, 1 year, okay, in 2011. And then you can say this is FTO forecasting then optimization. This is the method for end-to-end modeling. And this is the method if the forecasting is perfect. So that's the ideal cost. So we can calculate improvement of our proposed method compared to forecast then optimization. So you can say overall there will be 0.4% improvement for this kind of operational cost. It means we can achieve about 100K cost annually if they share this kind of data with each other. And then we can also calculate this kind of we can calculate the Shapley value for different kind of systems and determine the data value of this kind of collaboration. So you can say for the collaboration combination, we have different kind of combinations, and then we can calculate it. So actually, you can say the heat so you can say electricity sector makes little contribution. Electricity sector make this little contribution. So the improvement, so this kind of profit allocated to electricity is fewer because the accuracy of the electricity sector is relatively high. So the derivation of the electricity price and also the derivations of the electricity price in intraday and also the day ahead is relatively small. So the contribution is much smaller. But heat sector cooperate with the multiple and system operator cannot improve this kind of additional profit because it shows large randomness. So we have to consider this kind of uncertainty and also the complexity of this kind of heat sector. So that's the final profit allocation. And we can also calculate, we can guarantee the allocation failures. So you can say the heat sector enrollment can significantly reduce the operational cost. So it will allocate largest share of profit, about 100. And also the electricity make the least contribution, so it corresponds to the least share of profit. We can also say the incentivized effect. The electricity and also cooling sector, actually we can see the improvement of the forecast accuracy and also the modest profit. So for this kind of market, we have to consider the real world implementation. For example, they can sign the data sharing contract first before this kind of operation. And we also have some pricing signal and also the exit mechanism for this kind of market so that flexibly change their strategies. And we should also consider the cost of data sharing, even though in this case, we distribute all this kind of additional profit to different kind of sectors. But we need to also consider this kind of data, the running cost of data market actually can be easily done by deducting the cost from the additional profit. And we also need to develop the platform to support the real-world applications. So for example, we need a well-developed software platform for this kind of market. And we actually currently this is a centralized market. So we can reduce this kind of communication requirement. So the last part is conclusion and future work. So you can see in our work, the construction of a data market is a promising solution that would allow for a well exploration of data value. We propose an end-to-end data valuation approach for fair allocation and incentivization for different sectors. But in the future, we will actually, we have to say it's just on the very preliminary stage for data sharing. We will need to develop off-the-shelf data sharing platform to facilitate the cross-sector data sharing and also cross-enterprises sharing. Okay, that's all my presentation. Thanks.
Yi, thank you. That was a very interesting presentation. We should now move to Carla. Carla, are you ready?
Yes. Can you hear me? Okay. Can you see the slides?
Yes. Just one note, everyone. Don't forget, if you want to make questions, you can make them at any time. We see them in the Q&A section. So eventually we will answer them by the end of the presentations. Don't forget to leave your questions.
Okay, so thank you, Ricardo, for introducing our presentations. So this presentation is also about the creation of incentives for data sharing. So just to reinforce the message, why do we need incentives for data sharing? Well, there are huge quantities of data being collected, and this includes in power systems. There are also many works showing the potential of combining data from multiple locations. And all this seems perfect, but the problem is that data are collected by multiple individuals or companies that usually are unwilling to share their data due to personal or competitive factors. And because of that, we need to create incentives for data sharing. Data privacy is a mandatory requirement, but it is not enough because the benefits of data sharing are not the same for all data owners. So we need to create algorithms where data owners are compensated for the data they contribute. And the data, I don't mean quantity, I mean quality. So in this slide, I summarize some possible incentives for data owners wanting to improve their forecasts with data from others or receive some compensation to share their data. The first possibility is the monetary incentive, where data owners are willing to buy forecasts and pay according to their accuracy and or receive monetary compensation related to the impact of their data on the others' collaborative forecasting models. The second possibility is to promote an equitable data exchange, and in this case, no money is involved, and data owners exchange data with approximately the same value. Here, the challenge is how to measure the value of the data. And then we can also have other solutions where we share data because we will get some recognition, credit, or service. This is what Google does with us when we, for example, share our opinion about a place. When we have a recognition, like we can be a local guide, level 7, 8, whatever, and we also have a service to see what others think about a place. Our focus has been on data monetization and equitable data exchange. And in this presentation, I will present two of our algorithms, one for monetization and the other one for equitable data exchange. The focus is on regression problems, but solutions can also be extended to classification problems. So, regarding data monetization, I will present our simplest approach, starting with a very simple bidding strategy. So we have agents willing to pay up to a certain value for a more accurate prediction. We have agents willing to share data if they receive a certain compensation. They say the compensation they want. And to ensure data privacy, we have a trusted third party that receives all information, data and bits, and train the best model constrained by buyer budget. And if the model is linear, then we want to allocate the best model such that the sum of the costs associated with the coefficient. So if the coefficient is non-zero, then it has this cost. So the sum of the cost should be smaller or equal to the buyer budget. To solve this problem, these authors here have proposed an efficient iterative solver that uses a sequence of 0, 1, and accept problems. So it's an allocation problem as well. However, so it seems a good solution, but as you know, the linear assumption in this model, it's not a good idea. We know that usually this linear assumption does not work well in real use cases. And to deal with that, we have formulated the problem as an additive linear model where each variable is transformed with certain functions. For example, x1 is transformed in x1 power 1, x1 power 2, x1 power 3, etc. The same for the others. And then we have to do some adaptations on the prices. Here we assume that the package of all splines associated with a certain variable has a unique cost. So if variable P3, the original one, X3, costs P3, then we assume that if at least one of the splines associated with X3 is used, then the buyer should pay P3. So if two splines associated with X3 are used, buyer still pays just P3. So it's an assumption, we can change it. And that's it for this. The problem of this solution is that it is very easy to explain to the user. So you just have to bid how much you want to pay, maximum, how much you want to receive exactly if your data are used. But it is not very flexible for data buyers because their willingness to pay should depend on the quality of forecasts they buy. So they want to pay probably according to the improvement in root mean square error, for example. So we now assume that data buyers can specify their bids according to the accuracy improvements, and then the market operator has to train the collaborative forecasting model for multiple budgets, estimate the gain, the accuracy gain improvement with cross validation, and then take the bid that corresponds to the maximum expected gain. And what I mean is the green curve is the curve that the buyer selected. So it means that for a bid of 10, so he is able to pay 10 if the gain is at least 19. He is able to pay 30 if the gain is at least 41%. And then the market operator runs the previous model for a buyer budget of 1, 2, 3. So we construct these dots and then see what is the maximum gain inside this acceptable region. And in this case, this would be the acceptable price, the final price for this specific buyer. In this situation, we can see that there is no estimated gain between acceptable region. So this buyer will not buy forecasts because forecasts do not meet its expectation on gain versus final price. Okay, so we evaluated these algorithms with the real wind power data from the GEFCOM competition, where the goal is to generate wind power forecasts for the next 24 hours in 10 zones, 10 Australian zones. And we have as predictions 4 variables, which are the zonal and meridional wind components for 10 meters and 100 meters above the ground level. So we assume each data owner has 4 variables, and that's it. So and first we compare. We are assuming these additive models. So first we need to check if collaborative forecasting is better than local forecasting, and if these additive models are competitive with other state-of-the-art methods. So what you see here is we compare these additive linear models with kernel regression, gradient boosting trees, and also with lasso linear model that behaves worse. So here we see the root mean square error. So the behavior is much worse for the linear model than for the others. And then we also have dashed lines for the local version. So each model is trained using only data for the specific region, and also using data from all regions to see if the collaboration helps or not, decreases the error or not. And the main conclusions is that in general, collaborative models outperform their local counterparts. Improvements vary significantly between zones. So zone 1 has a clear advantage, while zone 5 and zone 9, the local and collaborative forecast is not that different. So these differences justify the fact that we really need to create incentives other than privacy, because the benefit really depends on the zone. And we see also that spline lasso has competitive results when compared to kernel regression and gradient boosting regression trees that are non-linear models. And it has the advantage that it is much faster to train and to do forecasts. Now, in these slides, we show some results for the incentive mechanism we presented before. So each data seller has 4 features, as I said, and the bid is 1. So they fix a cost of 1 per each variable. Then the data buyers offer 3 different valuations. This VF1 means that the data buyer is willing to pay the maximum, which is 36, because we have 10 zones, each has 4 variables, so we have 14 variables, but 4 are owned by the own data buyer. So the maximum payment is 36. So here he pays whatever is needed to have the best model. In the value function 2, he is just able to pay $10, 10 cents. And in value function 3, he offers something like that. So it depends on the gain. While the first 2 are fixed values, the third depends on the gain. And the main conclusions are that higher buyer budgets lead to better performance. Higher payments are associated with the higher gains. So agent 1 pays more, but he has a higher gain, and data owners improve their accuracy and or receive a monetary compensation for sharing their data. So the market seems to work well as an incentive for them to share their data. So we submitted this idea in early April. So soon we hope the paper will be available and the code as well. Now, regarding our developments for this equitable data exchange, now we also have multiple agents, but they all have a target and at least 1 covariate. And they are willing to share their data if they receive data with similar value. And again, we have the market operator that receives the data and tries to maximize the total value exchange between agents subject to the fact that the difference between shared and received values should not surpass a certain threshold, because we will not have exactly the same values too. So this difference will not be zero, but we can put there a threshold. And we also need to make sure that we are not allocating redundant features, because we are looking here, for example, for spatial temporal data, and near locations can be really, really correlated. So if I take data from one location, I don't need the other one. Mathematically, it is something like that, so I will not go into details, but the funny part is that we can decompose this absolute value here as two conditions, and then we have to solve a linear problem that we can solve with Python, with SciPy library, for example. So it's easy to solve and fast. But we have a problem. So we are assuming that we have this value, and then we want to maximize the location of value, but how to measure the value? Which metric should we use here to measure the value? We have explored multiple metrics. Here we have just some examples. We have some model-dependent metrics where we have Shapley values, feature importance, for example, and we have some model-free metrics like partial correlation, Pearson, although it measures linearity, the Candles, Spearman, they measure more monotic relations. And then we have conditional mutual information, which is a bit more robust. And to make sure that we are not accumulating too much irrelevant data and data that is already owned by the own data owner, we do some permutation tests to evaluate the significance of this correlation. So if the correlation or the conditional mutual information is non-significant, then we automatically remove the feature, the relation, and it's less a thing to decide. So it's automatically removed because we already saw it's non-relevant. So we tried all these metrics. We did many synthetic evaluations with very different relationships between data. Synthetic just because we want, in synthetic data, we know exactly the right relevance of the features, and we can see which metrics are behaving best. So in fact, these are, if we use the correct model, these are the best ways to evaluate the value of a feature. But as I said, it is model dependent. And after these two, we have conditional mutual information, which also performs very, very well. And because of that, I present here the results of this equitable data exchange, also for the GEFCON 2014 data using conditional mutual information. Here we can see for each of the 10 zones what would be the root mean square error in January using only local data. Here would be the best case scenario where everything is exchanged. So they have the maximum potential of collaboration. And here is what happens if we do this thing of equitable data exchange by measuring value with conditional mutual information. So the values make sense. We see that zone 1 has higher root mean square error improvement. And we see that zone 1 exchange information with all the others because he needs to receive from all, and to keep the balance between shared and received, he exchanged even small value variables because some relations are a bit weak. He did it, so he exchanged this zone exchanged data with all the others. We see that zone 2 has the second higher root mean square error improvement and the second higher shared value. I forgot to mention that I also have here a column, which is the shared value. And we see that zone 1 has the higher potential to improve forecast and share the higher value than the zone 2. And then the others do not have this potential, so they exchange less information. And to conclude, collaborative forecasting has this potential to improve forecast accuracy in many use cases, especially when we have spatial temporal data, and renewable energy, for example, depends on a lot on weather patterns. Data sharing incentives are fundamental to promote such collaboration, but as he already said, and Ricardo, data is a challenging asset because it has no replication cost. I can collect a feature and then sell it to multiple data buyers without an extra cost. The value highly depends on which other data are available because of this redundancy. And the value also depends on the buyer and its target. Incentives explored by our team, we have this data monetization. We have other approaches as well. We are now trying to extend these approaches also for classification cases. And in equitable data exchange, we are also exploring other use cases like the fail detection by combining data from multiple producers. And that's it. Thank you. And thank you also to my colleagues that worked with me for these incentives. Thank you.
Carla, thank you for this. It was really interesting. We have some questions already. I may reorganize the order of the questions just to start with some, let's call it quick fire questions. So answers, questions with quick answers. So the first one is for Carla. So in your case, can one data owner sell to multiple buyers or not?
Yes.
Okay, so
if the question is about the first algorithm, so if agent 1 asks for P1 each time so each buyer that uses his data should pay P1. So it would be P1 times the buyers that use his data.
Mm-hmm. And also, I'll make another question on top of that. So in this case, only buyers can make bids. So do you have a plan for a version in which sellers can also have bids? And
these value functions and yes, so we are working in something that we call social offer maximization, where basically we want to solve the collaborative forecasting model in such a way that we maximize the value function of buyer as it is now, and the seller, where the value function of the seller should be a function of the relevance of his data. So we can say if my data is just is contributing just for a small value, then I'm okay receiving 1 cent, but then if it increases, I want more.
Okay. Second one is if there is any coalition accepted in the data exchange methods. If not, what's the role of Shapley model? So do you accept coalition here? What happens if it exists?
So do you mean for the monetization incentive? Between
agents participating in the market.
Yeah, so we have this lasso term, so probably I didn't say it because we had this time restriction, but we train these additive linear models with lasso penalization. So if there are similar data, what the market does is it selects the cheapest option. So if 2 features are very relevant, but one of them is cheaper, then the model will take the cheapest option.
Okay. I think it's answered. We have many questions right now. So maybe for Yi. So considering that you have in your proposed framework, you have a regression model making the forecast and then an optimization model. Are you planning to use the forecasted value as a point to start the optimization? And is there any guarantee that the gradient will come towards optimal solution instead of going in opposite direction? So the combination of the two problems, how can one influence the other?
So it's a good question. Actually, in our work, usually we will do forecasting first, and then use the point forecast as the input of the optimization model. So actually, even though there's no theoretical guarantee that the gradient will come towards the optimal solution instead of going in opposite directions, but we do a lot of simulations by Monte Carlo sampling or simulation. So we can say with larger forecasting error, the operational cost will be higher, but it's not the cost curve is not symmetrical, and also it's not a quadratic function. This is the reason why we develop end-to-end model, so that we can integrate forecast model and optimization as a whole instead of separate these two separate as two separate procedures. Okay.
Yeah, I think this is actually a very real challenge, because even on the electricity market, agents often you can imagine that agents should have perfect forecasts, but sometimes it's worth more to overestimate or underestimate depending on the market conditions. You might earn more doing that and buying more energy than you need, or less, depending on the overcost of the market. So consolidating the two problems is an interesting approach. So we have more questions. I believe this is for Carla. Is there any scalability issues for your solution when a large number of data providers / buyers are present?
Well, it gets slower if we have more data owners. We didn't test exactly the limits, but the solutions are fast, and we are also applying this. As I said, we do, for example, the correlation analysis or the conditional multimodal information. Then we do the permutation tests to see if these values are significant or not. And if they are not, we automatically remove data. And with this, usually a lot of data is removed. Many features are removed, especially in geographical data that is really close, because since we condition to the variables that the owner already has, when we condition, we automatically remove a lot of data.
Yeah, so you kind of remove buyers with similar information, and redistribute the revenue based on that similarity also, right? Afterwards. Okay, so for E, it's a big question, but I'll try to read it all. So I understand that in a newly created market, such as the data market, the monetization and boundaries might be guided. But evolving to a more mature market, it should be market driven. Don't you think elements such as the volume of purchase of a certain dataset type, quality, relevance, and uniqueness of the data should play a role in the monetization exercise? I think you have also something on this.
So I can answer this question first. Actually, for all the market, the price is perfect. That is, the price is the same as the value. If the price is same as the value. So all the work I introduce or Carla introduce is to find the real value of this kind of data. But for market, we want to establish market to recover this kind of value, even though it's not exactly the same. Maybe we want to establish market that as near to as much near as possible to this kind of real value. So actually, you say that the certain data set type, the quality, relevance, and the uniqueness of data, actually all these are related to value. For example, if I have 10 years data and you have only 1 year's data, but the model trained based on this 1 year data has high accuracy, then it has high value. Yes. So is related to that. But we, from a theoretical part, we want to load value. But for a market part, maybe we want to recover discount value by discount pricing schemes. Yeah.
I think this highlights the value of having a proper data value assessment layer in your frameworks. Because if you look just at the volume, it might not be important if the data is always the same throughout the years, for instance, and if you just have the not relevant data to train a forecasting model. So that value assessment layer is very important. And I think this is also highlighted in your paper. So I think whoever made the question, it's anonymous. They could also give you a read to your work. So we have more questions. Okay, how much, I think this is for Carla, from Rachel Wilson. How much you account for the fact that data has more value the more it is combined?
The more it is combined, I'm not.
I don't know if this is the question, but your data might have no value if combined only with data from another person, but might have more value if combined with data from 2 or 3 or 4 other persons for the forecasting model, due to the cross effect between the input variables. We can account for that in this type of framework, no?
Yes, we are working on that. So right now we are trying to extend this monetization solution to have, so we apply splines for each feature individually. We don't have the cross effects, but in reality, they probably happen. So we are now extending our solution to consider also cross effects. And then in terms of formulation, it means that instead of solving solving linear knapsack problems, we will solve quadratic knapsack problems, but we still don't have the final solution to see what is the impact of considering mixed effects in our models.
Okay. Perfect. So here I think this might be for Carla also, but maybe also applicable to E presentation. So a recurring payment system could be implemented. This would incentivize data owners to share justified by a potential recurring future payment. So instead of having just a payment session by session or forecast by forecast, they would have just a monthly payment. So they are incentivized to keep buying and participating. Maybe Carla, you want to start with this, elaborate on this?
So I think you mean by on the buyer side, they have a fixed quantity, and then data sellers just collect a proportion of this payment according to their relevance for the model. It's a possible solution and it might work. But in this case, data sellers do not set their preferences. They will just receive whatever it is decided, and they don't have like a minimum. Like I want to receive at least this value, but it's a possible solution. Yes.
Okay. So this is also considered. Another extra question. So regarding, and this is more for you. So one important aspect to consider also on when sharing data with other entities, and even when for the use case that you talked before. So in China now you have data exchange centers.
Yes.
Data traceability is an important question for the future, right? So now that we have blockchain evolving and that we have data spaces appearing, how do you see this evolving in the future? So my data is sent somewhere and I want to know, or not, what happens with it afterwards.
Yes, it's a good question. Actually, maybe for example, in the data market in different kind of cities in China now, they just okay, I have this kind of data. You can buy this kind of data according to the quality, the number, the quantity, and also the quality of this kind of data, they can set price. And then if you are willing to buy this kind of data, then you can pay for that. So, but in the future, especially in for example, especially in any systems, which, for example, smart meter data, it can be stored or distribute in a distributed way, and we can also have access to this kind of data from in the cloud or something like that. So we have different way to store. We have different way to get this kind, download this kind of data with some limited with some how to say, for if we want to have a fair market, or maybe this kind of we may need to how to say formalize this kind of procedures in the near future, and also consider security of this kind of data. This is also the work we are working on. For example, using blockchain and also using encryption method to encrypt this kind of data or something.
Okay, and also just to finalize, and a question on my side, and for you, so you talked about real-world implementations. So right now, it is a centralized approach, but considering that we're talking about training a neural network to solve an optimization, to then solve an optimization problem with the result of it, could the training of the neural network be done in a federated environment? So,
Yes,
yeah.
Great. So actually, that's our next step. For neural networks, it can be trained in a federated way. For the optimization model, for example, ADMM can be used to solve this kind of optimization model. So how to combine ADMM and also federated learning in this end-to-end model, that's a problem. Yes, it's a new problem.
Okay. Well, I think we do not have more time. We still had some questions to answer, but we are on time. Sorry for whoever was left out of the Q&A. And thank you for all the questions. So just some final remarks. So the work that Carla has done, part of it is also open source on our GitHub from the Center for Power and Energy Systems at Inespitec. So I invite you to give it a look. And also a big thank you for Yi and Carla. Those were very nice presentations and important topics. And a special thanks, of course, to everyone. Sorry again for the technical difficulties in the start, but hopefully you enjoyed the presentations. So quick wrap up, we will send you all a link with this session recording. And you will eventually later be able to find it on YouTube. Don't forget to check our website for future webinars and also for the past webinars. And again, if you want to participate on a future webinar or attend to future webinar, just please let us know. Danielle just posted the links on the chat. So I think we have all information that we need. So thank you all and have a nice weekend.
Thank you.
Thank you. Bye-bye.